All right. Good afternoon. Uh, okay. Still continuing on with what we have regarding functions, and I had mentioned last time that we would be looking into variations of the concept of slope, and now for what we have in the case of what is referred to as the average rate of change of a function. Okay, so this is a formal functional notation for what we otherwise refer to as slope. And just referring to a graph, okay, that we have on page 163, okay, and we have just concerning the average rate of change of a function, okay, at least if you take a section of the function, and we have from this graph, okay, you have a curve, okay, or sort of like a parabola that is opening downward as indicated by the downward pointing arrowheads. And this particular item refers to like the slope between the points on the parabola where we have at 1, 6, and 5, 2, and you're looking at the slope, or in this case, the average rate of change on that particular curve, and just taking a straight line through this, okay, just sort of connecting the dots with a straight line, and that line is referred to as a secant line. And that line is passing through 1, 6, and 5, 2. And for what we have regarding the average rate of change, this is just a functional notation for what we refer to as the slope. And we have, just by a bit of a definition, okay, we have the average rate of change of a function, which we have at y is equal to f of x going from x1, y1 equals x1 f of x01. So the functional notation for what we're referring to regarding the coordinate y1. Remember, y is equal to f of x, and in terms of the points y1, you have f of x of 1. For the second ordered pair, okay, we have x of 2, y of 2, and so we have x of 2, f of x of 2. And the average rate of change of a function, in this particular case, you have the slope m, and you have m, and you have the subscript to SEC, and that's just in reference to the secant line. Okay, so you have the secant line, SEC, for the slope of that secant line. And again, you are still carrying out the concept of slope. Again, you have y of 2 minus y of 1 all over x of 2 minus x of 1. And again, just for the functional notation for the vertical change, again, we have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. And again, for the change to be defined, we cannot have a zero denominator. And so we have that x of 1 and x of 2 cannot be equal to each other. So we have, in the case of the graph, again, we had the point 1, 6. We have x of 1, y of 1, or which could also be referred to as x of 1 and f of x of 1. For 5, 2, we have x of 2, y of 2. And we have, in functional terms, we have x of 2, and where y of 2 is f of x of 2. So for the average rate of change between these 2 points, again, we have the slope of the secant line. And so we have, again, the vertical change. You have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. And just filling in, so you have 2 minus 6 for the change in the functional value all over x of 2 minus x of 1, which we have at 5 minus 1. So the amount of change vertically, okay, we have a drop of 4 units, and the horizontal change, you have a rightward shift of positive 4 units, and we have negative 4 over 4 is equal to negative 1. All right. And so again, just the average rate of change of a function, that's just formalizing what we refer to as slope. And now, when would you use this formula, so to speak? Okay, now the traditional slope formula, okay, it's automatic, like in the case if you have looking at the slope of a straight line. But if you have, again, if your graph is not a straight line, sort of like a curve, then you apply the slope of that curve, say for 2 specified points, and this is where you have what we refer to as slope, kind of put into the lingo of what is referred to as the average rate of change of that function. And let me just kind of show you where the dynamics can sort of play out regarding the average rate of change of a function. And we'll say that if we have a function, and we'll say that we have y is equal to f of x, and we have is equal to x squared plus 2x. And let's say that if you're looking at determining the average rate of change So you're looking at the average rate of change, okay, of this function. And say we're going from, first of all, okay, we have going from x equals 1 to x equals 5. So that's one average rate of change, or one slope calculation. And also you have, say, going from the same initial point as we go from x equals 1 to x is equal to 9. Okay? And just sort of getting things set up. So again, we have for y is equal to f of x is equal to x squared plus 2x. Okay. And okay, so just starting out, okay, we have going from x is equal to 1. So in the case of what we have at x is equal to 1, okay, so for the corresponding y value, okay, you have f of x, okay, becomes f of 1. And x squared plus 2x becomes 1 squared plus 2 times 1. Okay, so 1 squared is 1, 2 times 1 is 2, and 1 plus 2 is 3. So you have a point on the graph of this function, and that would be 1, 3. Now we have x equals 1 to deal with. Also we have x is equal to 5 to work with. So you have y is equal to f of 5. And for x squared plus 2x with x at 5. Okay, so we have 5 squared plus 2 times 5 is equal to 25 plus 10 which will be 35. And so on the graph of this function, along with 1, 3, okay, we have 5 and 35. And if we go ahead and determine the function value whenever x is equal to 9, so y is equal to f of 9, and then carrying over, I have 9 squared plus 2 times 9. 9 squared, we have 81. 2 times 9 is 18. And 81 plus 18 comes out to 99. So we have for this particular point on the graph, okay, along with 1, 3 and 535 would come out to 999. Okay. And then just kind of going back to the average rate of change question. Okay, so we have in part A, okay, Okay, so as we are looking at going from x equals 1 to x is equal to 5. Okay, so you're really looking at in terms of ordered pair settings. Okay, so at x equals 1, okay, so you're going from 1, 3 to 5, 35. And we have just for the average rate of change, again, that's going to be the slope of the secant line. So again, we have f of x of 2 minus f of x of 1 we have all over x of 2 minus x of 1. So, and setting up what we have for the difference, okay, so f of x of 2, that'll be 35. And you have minus now for f of x of 1, that is your first y coordinate. So you have f of x of 2 minus f of x of 1, that's 35 minus 3. X of 2 minus x of 1, okay, that's going to be 5 minus 1. So we have 35 minus 3, that is going to be 32. 5 minus 1 is 4. So between x equals 1 and x is equal to 5. In other words, if you had a straight line connecting 1, 3 and 5, 35, the slope is going to be at 8. So that's going to be the average rate of change of the function between those 2 points. Now, as we go further out along the y-axis, okay, and we still have going from the same starting point, and this time going beyond x equals 5 out to x is equal to 9. Okay, so we have going from 1, 3 and at x equals 9, so that means you're going from 1, 3 out to 9, 99. And for that particular rate of change, so again, you're still looking at change in y values with respect to the change in the x. Okay, so you have going from 3 to 99 in y, so amount of change, you have 99 minus 3. And in the horizontal, okay, we're looking at 9 minus 1. So to go from y equals 3 to y is equal to 99, we have an upward shift of 96 units, and then to go from x equals 1 to x equals 9, you have a shift of 8 units, and we have 96 divided by 8 comes out to 12. Okay. And notice we have a different rate of change. And to provide a little bit of a visual, okay, so again, average rate of change is just a way of saying slope between or connecting or going through 2 points, and just looking at the dynamics. And yeah, I had this graph in store. Okay, so you have for this item, so for that curve which we have in red, okay, this is going to be in reference to, again, y is equal to f of x is equal to x squared plus 2x. Now where the secant lines are concerned, okay, so if you notice, we have with the graph, okay, so you have included on the graph, you have 1, 3, 5, 35, and 9, 99. And we'll say that for the secant lines. Okay, so going through 1, 3 and 535. So again, just for the secant line, the average rate of change, okay, between 1, 3, and 535, both points on the curve, the average rate of change of that curve between x equals 1 and x equals 5, again, we have at 8. And for this function, as x gets larger, okay, so going from 5, x equals 5 to x equals 9, okay, notice that the slope becomes steeper. Okay, so for what we're going to have in effect, okay, so we're going out further in x. And if I can just stretch this out just a little bit here. Okay, so we have with the slope of that secant line, again, that is equal to 12. And so for the average rate of change of this function, as x gets larger, the slope, connecting 2 points, especially from the starting point, it's going to get larger and larger. So if I went out to say x is equal to 20, then to 50, and then to 100, the average rate of change will continue to get larger. And as x expands continuously, the average rate of change is also going to go up continuously. And if x gets so large, it's almost as if the average rate of change is going to be tending to infinity. All right. So this is just a sample of what we have regarding average rate of change of a function between an initial point and final destination. Okay. And now, just some items that we have, again, along with functions and their individual characteristics. We're now going to cross over to looking at operations that exist between functions. And so we have in this case, right? So we have our operations between functions. And we'll start out with the more basic 4 operations. You have adding, subtracting, multiplying, and dividing. And now we have just see we have for 2 functions. Okay. And it could be all kinds of combinations, but we'll say that with a pairing. We'll say we have f of x once again, and we'll say that the other function will be g of x. Okay, so for functions, f of x and g of x. Okay, we have for operations, okay, and just to show you the bit of coding that is done, we have for what's referred to as the sum function. Okay, so we have shorthand, we have f plus g of x, and that would translate out to taking the sum of f of x and g of x. And you would have the arrangement of the functions in the order that they appear. Like if I had g plus f of x, I would have g of x plus f of x. And for the difference function, okay, so you have for f minus g of x, okay, so this is going to become f of x minus g of x. And then for the product function, okay, if I have, let's say, f times g of x, so we're going to have f of x times g of x. And then we have with the quotient function, we have for f over g of x. Okay, so this will translate out to the quotient, whereupon we have f of x divided by g of x. And again, when we first looked into functions, we also had looked into domain. And for the domain of operations that exist between functions, let me mention, okay, now for the sum, difference, and product functions, okay, these first three operations, the sum, the difference, and the product functions, okay, they're going to have the exact same domain. And this domain is going to be formed by combining the restrictions, if any, of f of x and g of x. Okay, so you have the first three operatives, okay, have the exact same domain, again, which will be formed by combining the restrictions okay, if any, of f of x and g of x. Okay. Now, for the quotient function, okay, now in this one, okay, say if you have f of x and g of x provided as direct functions, okay, okay, you don't have anything like fractions or even root radicals imposed, at least not in the general notation for the sum, difference, and product functions. So you're going to have sort of the pattern where these are going to have the exact same domain. But with f over g of x, okay, now we're not given specifically what f of x or g of x will be. We're just looking at the general case. But you already have an imposed restriction that whatever we have between the functions, right away, g of x cannot be equal to 0. And it's because of this already laid out predestined restriction that the quotient function can have a domain that is different from the other operations. and we'll say that we have, for instance, say if we have a couple of linear functions. Okay, so you're looking at the sum, difference, product, and quotient functions. Okay, so you have determining the resulting functions and their domain. And we'll say that we have given let's say we have f of x is equal to 3x plus 7 and g of x, okay, we have equal to 4x minus 8. Okay, so looking at the results here, okay, and we have in the foundation, okay, so you have f of x, you have a linear function, okay, so this is like saying y is equal to 3x plus 7, and for g of x equal to 4x minus 8, okay, you have another linear function, okay, at y is equal to 4x minus 8. Now, in the case of what we have with the operations, okay, and so just kind of copying what I have here. So we have with first case, right? So you have the sum function, and you have f of x plus g of x. Okay, and now with f of x and g of x specified in this example. Okay, so you have from f of x, I have 3x plus 7. I got plus g of x, so g of x. I have 4x minus 8. And the reason I'm using parentheses here is just to draw out what f of x is, and also drawing out what g of x is, and just noting the separation of the functions with the addition. Okay, so we're going to have, in effect, okay, so there will be no sign changes. So you have 3x plus 7 plus 4x minus 8. And if we combine the variable terms, so this will come out to 7x. And the constants, we have 7 minus 8, which will be negative 1. So we have, in this one, okay, so we have the sum function with what we have for f of x and g of x. This will come out to 7x minus 1. Now, for what we have in the case of the difference function, okay, so we have f of x again. We have 3x plus 7. You have minus g of x, so we're going to be subtracting all of 4x minus 8. And once we remove the parentheses, okay, so you have 3x plus 7. And then now, again, I'm using parentheses to separate the f of x and g of x. Now that we have subtraction in the middle, okay, upon removal of the parentheses, okay, so you have 3x plus 7. Now for 4x minus 8, those terms will be affected by the subtraction in front of the g of x, so 4x becomes negative, and what was the subtraction of 8 is going to translate out to addition. And so combining terms, we have 3x minus 4x becomes negative x. And you got plus 7 plus 8, which is going to be plus 15. So you have negative x plus 15. Now for what we have in the case of the product of the functions, so we have 3x plus 7, again from f of x. We have times g of x which we have at 4x minus 8. And looking at distributing, okay, so you have 3x times 4x, so we have 12x squared. Outside product, see, that will be negative 24x. Inside product, have 7 times 4x, so this would be a 28x. And the last product, we have minus 56. And we have for the results here, okay, we have the outside and inside product terms to combine. So we have, after 12x squared, we're going to have plus 4x minus 56. And for what we have for the quotient function, so we have for f of x over g of x, okay, so we have f of x at 3x plus 7, and g of x we have at 4x minus 8, and okay, and the greatest common factor between the terms is only 1, but in terms of anything to factor that will be shared between the numerator and denominator, we don't have any such case. All right, so just the substitution of 3x plus 7 into f of x and 4x minus 8 for g of x, okay, that quotient function is already in simplest terms. Now, in the case of what we have concerning the domains, okay, so again, for f of x and g of x, okay, now f of x and g of x, both of these are linear functions. You don't see a fraction, and you do not see anything like a square root or any other kind of even roots. So we have for f of x as well as g of x, okay, you're not going to have any restrictions. So for f of x, because that single function has no restrictions, okay, now the domain is going to be the set of all real numbers. Again, g of x, okay, you have no restrictions, and the domain is also going to be the set of all real numbers. And for what's going to happen, okay, is that it's kind of going back to what we have regarding the sum, difference, and product functions. Okay, their domain will be formed by combining the restrictions, if any, of f of x and g of x. Well, guess what? There are no restrictions for f of x or g of x. So that means that automatically, since there are no restrictions for either of these functions, there will be no restrictions for the sum, difference, and product functions. Okay. So again, we have the set of all real numbers throughout. Okay, so again, because we're able to work with, for all of these functions, with f of x and g of x for all real numbers. Now with f over g of x, okay, this, again, it has to play by the added rule that the denominator cannot be 0. Okay, so for 3x plus 7 over 4x minus 8, okay, the 4x minus 8 cannot be 0 in value. And if that is the case, well, we have that 4x cannot be equal to 8. And so we have that x cannot be equal to 2. Okay, so while the domain of the sum, difference, and product functions will consist of all real numbers, it will, however, turn out that for the domain of the quotient function, we have almost all real numbers. However, 2 is going to be excluded. And if I were to take what I have for the domain and express in terms of interval notation, so 2 is going to be left out. So you think of graphing like you have a whole or open circle onto, and then just have a ray to the left and a ray to the right, both rays going continuously. So we would have at the lower end, you have from negative infinity approaching, but not including 2. And then you have at the upper end, you have going past and not including 2, heading on out to infinity. So again, for the first 3 operations, we have all real numbers. And then for the quotient, again, we have, again, one restricted value with 2. So that means you have those values less than 2 and those greater than 2 united, okay, to represent the domain. All right, and tell you what, just for what we have in the case of so we're looking at resulting operational functions and their domain, and we'll say that we have given, we'll say that we have f of x is equal to x squared plus 1, and we'll say that g of x is equal to x squared minus 4. Okay, just for what we have given, f of x is equal to x squared plus 1, and g of x is equal to x squared minus 4. Okay, so if I look at the operations between the functions, so we have for the sum function, okay, so we're looking at adding f of x and g of x. So f of x, again, we have at x squared plus 1. We have g of x, okay, so you have x squared minus 4. And so if we add together, so you have x squared plus 1 and x squared minus 4. So we have x squared and x squared will form 2x squared and 1 and minus 4, so we're going to have a minus 3. So for f plus g of x, okay, we're going to have 2x squared minus 3. Okay, and depending upon the nature of the individual functions, okay, now a sum function can result where once you combine or add the terms, you can have the output to be subtraction, as in the case of 2x squared minus 3. And you can also have a difference function to end up where the unification of f of x and g of x will end up being a sum of terms. So we have with f of x minus g of x, so we have x squared plus 1, and we have minus, okay, we have all of x squared minus 4, and taking out the parentheses, so we have x squared plus 1, we have minus x squared plus 4, and guess what, this time around we're going to have x squared terms to cancel out, and we have 1 plus 4, which is going to be 5. Okay, so the result can end up as a constant and no variable term present. Okay, so again, we have for the difference of these functions, it comes out to 5. Now for the product function, taking f of x times g of x, so you have the quantity of x squared plus 1 times that of x squared minus 4, and applying the FOIL. So you have x to the 4th. Outside product, we have negative 4x squared. Inside product, we have positive x squared. Last part we have at negative 4. And we have a trinomial expression whereupon we will have x to the 4th minus 3x squared minus 4. And for what we have in the case of the quotient function, for f of x over g of x. So we have with f of x, we have x squared plus 1. And g of x, okay, we have a x squared minus 4. It could also express in factored form. You have x squared plus 1 all over x plus 2 times x minus 2. Again, the factoring in the denominator is optional because either way, okay, we have the simplified result. All right, and now for f of x and g of x. Okay, now these expressions are given in direct fashion. Okay, and so we don't have a fraction or an even root radical. So you have a bit of history to repeat. Okay, so for f of x and g of x. Okay, again, we have no restriction. And the domain, again, we have to be the set of all real numbers. Again, have the same thing for the sum difference and product functions. And once again, with the quotient function, in terms of the domain, okay, this could be the odd individual out. And here we have the restriction that the denominator cannot be 0 in value. So here we have x squared minus 4 cannot be 0. And if that is the case, then neither of the factors that we have with x plus 2 and x minus 2 can be 0. So we have x plus 2 cannot be 0. And we have x minus 2 cannot be 0. So we have that x cannot be negative 2. And that x cannot be equal to positive 2. And so just kind of giving a bit of a visual. So you have negative and positive 2 excluded. Okay, so you have holes at negative and positive 2. And just for the modes of activity, okay, so, and still excluding both negative and positive 2, so we have, again, you have values less than negative 2, and you have those values between, but not including negative or positive 2. And then we have for the remaining extreme, we have those values of x greater than 2. And so for what we're going to have in the case of the domains, okay, so we have for the domain of the quotient, okay, so once again we have with the 3 sections here, we're going to have those values of x that are less than negative 2. We have along with those values of x such that negative 2 is less than x is less than 2. And you have parentheses throughout. And then finally for the remaining stretch, we're going to have those values of x which are greater than 2. Okay, And once again, just notice, okay, for what we had before, there was one exclusion from the domain in the prior example. So you had two subintervals. And now for this quotient function, we have two exclusions with negative and positive 2 restrictions and the resulting interval notation for the domain. Okay, we had the inclusion this time of 3 subinterval sections. Now, right now, so far with all of the expressions we have had among our 4 operations have been in the general case. And it's now, in other words, general, where the input has been x throughout. But now let's say that if we're looking at determining functional values for specified inputs, and let's say what we'll just call this operational functions for and specified inputs. Or I should say operational functions involving specified inputs. And this time we'll take 3 functions. And we'll say that we have given f of x is equal to, we'll say 2x plus 3. G of x is equal to x minus 3. And say we have h of x is equal to x plus 10. And say we'll determine what we have for, let's say you have f plus g of 4, and we'll say we have f minus h of 7, and we'll say we have g times h of 5, and we'll say that we have let's say we have h over f of negative 2. Okay. All right. So we have just in the layout. Okay. So if we're looking at, and there are various avenues that you can go through. Okay. So we have in the first. Okay. So we have f plus g of 4. So this would translate out to f of 4 plus g of 4. And if I wanted to go ahead and tackle f of 4 and g of 4, this is one approach. So just like in lieu of x, you have 4. F of 4 plus g of 4. And, okay, now, if I wanted to itemize, okay, what we have for f of 4, f of 4, you have 2 times 4 plus 3. 2 times 4 is 8. 8 plus 3 is 11. In the case of g of 4, remember g of x equal to x minus 3. Well, guess what? G of 4 is going to be 4 minus 3. which is going to be 1. Okay, so if I relay this information over to f plus g of 4, so f of 4, again, we have at 11. You got plus g of 4 and g of 4. We have at 1. And for the resulting output, okay, this comes out to 12. So f plus g of 4 is equal to 12. Now for what we have in the case of f minus h of 7. So this is going to be f of 7 minus h of 7. So you have f of 7. Okay, so again, we're working with f of x, and with x at 7, so you have 2 times 7, which is 14. 14 plus 3 is 17. For h of 7, okay, h of 7, guess what? We have 7 plus 10. 7 plus 10 is equal also to 17. So for f minus h of 7, we have f of 7. F of 7 is 17. We got subtraction. Now h of 7, also 17. And we have 17 minus itself, and this outcome becomes 0. And for g times h of 5, okay, so we're looking at g of 5 times h of 5. So we have with g of 5. Okay, so g of 5, we have 5 minus 3. And g of 5 is equal to 2. For h of 5, okay, so h of x is x plus 10. Well, h of 5 is going to be 5 plus 10. So this is going to be at 15. So we have in the follow through. Okay, so you have g of 5 times h of 5. So that is going to be 2 times 15. And for the output, that is going to end up at 30. Okay. And then we have for the case of division. So for h over f of negative 2, we're going to have h of negative 2 all over f of negative 2 so h of negative 2, okay, so you have negative 2 plus 10, which will be 8. And for what we have in the case of f of negative 2, f of negative 2, so you have 2 times negative 2 followed by 3. Now 2 times negative 2 is negative 4. Negative 4 plus 3 is negative 1. And so we have in the follow through. Okay. So h of negative 2 is 8. F of negative 2, again, we have at negative 1. And we have 8 over negative 1, so this will come out to minus 8. Okay. Now, there are other operations we will be looking into, namely like like the composition of functions, and again, this will be just like just some remnant, and the dynamics will be a little different for those types of functions than what we have so far with the sum difference product and quotient functions. And now, again, the first three operations, okay, will have the same domain, and they'll be defined by the restrictions, if any, that are imposed upon the individual functions when you combine the limitations. Now let's say that, just as a case, not determining the operational functions throughout. Let's say if you're looking at determining the domain of the following. And let's say we have here so we have f of x is equal to 3 over x plus 4. And we have g of x is equal to, and we'll say x minus 4 over x plus 1. And keeping the same f and g of x. If I'm looking for the domain of the sum, difference, product, and quotient functions. Okay, so just starting out, okay, so for f of x equal to 3 over x plus 4, okay, now, again, we have a rational function, and again, for rational function, we cannot have a zero-valued denominator, so x plus 4 cannot be 0, so we have the x cannot be negative 4. For g of x equal to x minus 4 all over x plus 1, again, we have a couple of x expressions, but again, the focal point will be keeping the denominator, the bottom part, from equaling 0. Now, the top part can be 0 as long as the bottom part is not. And here, for g of x, x plus 1 cannot be 0, so x cannot be negative 1. Now, for the sum, difference, and product functions, again, they're going to have the same domain, and we're going to have combinations of restrictions. Okay, so to be able to work with f of x, x cannot be negative 4. And to be able to work with g of x, okay, x cannot be negative 1. Okay, so be able to add with and subtract with and multiply with both f of x and g of x. F of x has to be kept defined, as must g of x. So we cannot have x to be negative 4 or negative 1. And guess what? I'm still working with both f of x and g of x in the quotient function. So those restrictions are also going to apply. Because I still have to keep both f of x and g of x defined. Now, for the domains, okay, so f of x, x cannot be negative 4. So yeah, for the domain, okay, so you're looking at those values of x less than negative 4, as well as those that are greater than negative 4. And for g of x, okay, only -1 is excluded, so you have those values of x less than -1 and those that will be greater than -1. And for what we have with the sum, difference, and product functions, so both -4 and -1 are excluded. So you have 2 exclusions and 3 subintervals that you have sort of dancing around -4 and -1. Okay, now for the quotient function, we may or may not have the same domain. So in looking at what we have for this particular setup, again for f over g of x, we have f of x over g of x. Okay, now f of x, again we have 3 over x plus 4. For g of x, again we have x minus 4 all over x plus 1. So I'm still having to keep f of x defined. So again, x plus 4 cannot be 0. For g of x, x plus 1 cannot be 0. Now, in the rewrite, okay, so I've got a fraction dividing another fraction. And if I take care of the fraction over fraction, what I can do is that I can take the top fraction and have this to multiply the reciprocal of the bottom fraction. So dividing by a fraction is the same as multiplying by that bottom fraction's reciprocal. So this time we're going to flip x minus 4 over x plus 1 to where we have times x plus 1 over x minus 4. And so just looking at what we now have in the numerator position, we have 3 times x plus 1, and this time we have x plus 4 times x minus 4. And for the restrictions, again, x plus 4 cannot be 0, x plus 1 cannot be 0. And looking at the denominator in the final result, now we still have the x plus 4 cannot be 0. Now we have from g of x, x minus 4 was in the numerator position, but upon multiplying by the reciprocal of g of x, x minus 4 is at the bottom. And this time, because x minus 4 has been flipped to the bottom, we now have this cannot be 0 either, and we have the x cannot be positive 4. And so, along with x not allowed to be negative 4, as well as x not allowed to be negative 1, we now have the x is not allowed to be equal to 4. And so for the domain of the quotient function, we have more restrictions, so you're going to have kind of a long interval notation for the domain. So we have starting from smallest to largest. So you're going to have those values of x less than negative 4. After negative 4, okay, you have approaching negative 1. And after bypassing negative 1, we now have approaching not infinity yet, but approaching 4. And when we finally bypass 4, Okay, we have the completion of the domain of the quotient function, where we have those values of x greater than 4. Okay, so for the interval notation for the domain of this last operative, okay, we end up with 4 subinterval sections.